Alrighty. So my goal for today is to get as much progress on chapter 3 as possible. But because I'm behind on the labs, I'm going to start with doing this bomb lab. So I'm just going to close out of that, and we'll go over here to the labs, which are labs here. Get status. So I just modified bomb. I think this was just formatting. Yeah. Bunch of formatting stuff. So let's cd into bomb, see what we got in here. Okay, there's a bomb lab PDF, a README, a C file, and the executable. And basically my understanding from looking at this before is that the bomb.c calls into functions that aren't provided in code. So it's linked to some other object file that I don't have access to. So that requires me then to have this bomb executable that I've run blindly under GDB. So instead of just giving it full access to my computer, I'm going to spin up the Docker container, which I think was covered in here somewhere, right? Yeah, if I just run docker run, this is probably going to be boom. That'll probably be enough. Yeah. Okay. And then in here, I'll be able to run stuff. So I'll create another terminal over here. Actually, you know what I'm going to do? I'm going to... I want to start using tmux more now that it's fully supported. So that'll require me going into config hyperland. Was this look and feel? I think it's called. And then I'm commenting that out. And then when I close this out, that gives me the full screen, but with my way bar still visible. Okay. So now we can do our splits, and I want to do, oh fuck, I forget how to do this. It's Control B quote. How do I do the other way? I forget. Oh, there we go. Oh, man, I forget. My brain's not working this morning on tmux. Tmux cheat sheet. Because I always use the quote and then I use Control B space to reflow it, but like, where would that be here? Because I don't think Control space is the same on percent. Oh, how did I forget that? Control B percent. There we go. Okay. Yeah, this is using the tmux config for Omarchi. I'm trying to like just delegate everything to DHH on his setup and not like worry about configuring this stuff too much on my end. Because you can just spend your entire life just like obsessing about stupid stuff. So, okay, I got my Docker thing going over here. So Docker PS, try that again. Run. Okay, there we go. And then we go under, see it, yeah. There we go. Wait a minute. Doesn't seem right. This is under the wrong directory. So I gotta go over here, labs, bomb. I'll just call it bomb. And then I'll run docker ps here. And then cd. And then we got, okay, we got our bomb executable in a container now. So now we can go do the same thing here, labs, bomb. And before we get started on this, I want to, of course, read the README. This is x86 bomb for self-study students. Cool. Let's go and open up the bomblab.pdf. We'll go ahead and read this. This thing is 4 pages, not too much here. So, diffuse a binary bomb. The nefarious Dr. Evil has planned a slew. You know what I should do is run this thing under with no networking. So here, if I try like curl google.com, of course that works. But there's a flag man docker network. I think you just say network none. I'll do network is equal to none, and then curl google.com, and that'll just prevent me from prevent the bomb from like actually communicating out in the network. Okay, let's go back over to here and open the bomb lab PDF again. Because part of the bomb exploding is that it makes network requests. I just want to avoid that. So whatever I do, I also want to like trace it. I wonder if GDB has like the ability to trace. Let's ask AI here. I'm gonna throw that over there. Say, hey, does GDB have the ability to output all of the syscalls a process is making, similar to strace? MonoGDB has catch syscall. Okay. So if I say something like GDB bomb boot, oh, I need a CD here. GDB bomb, and then I'm gonna set a breakpoint at main, and I'm gonna run catch syscall, and then I say restart. Warning, error disabling address space randomization operation not permitted. Okay, that's fine. Catch point, that's just warning. Catch point 2, call to break. So it's just memory stuff. And you can see where this was compiled on as some relative directory. So it's trying to output the source and I can't find it. So that's fine. These are all catch points. Doing breaks, get set, access, access. Can I disable this and then continue at main? Yes. Let's rerun this. Set tech OVI, GDB bomb, and then catch syscall. I'll do that later though. First I'll break main. Break. Come on, what are you doing, brother? Break main. Restart. Okay, so we're at main. And this is probably not. This is line 37. Bomb.c. If we go down here, 37 would be, yep, that's where we want to be. And then if we catch, we can say catch syscall from there. So that prevents any syscalls from actually happening. So we can see the network request. I'm just going to continue from there. Actually, no, I'll leave that alone. Let's go ahead and continue reading. So, nefarious Dr. Evil has planned a slew of binary bombs in our class's machines. A binary bomb is a program that consists of a sequence of phases. Each phase expects you to type a particular string on standard in. If you type the correct string, then the phase is diffused, and the bomb proceeds to the next phase. Otherwise, the bomb explodes, printing boom, and then terminated. The bomb is diffused when every phase has been diffused. There are too many bombs for us to deal with, so we are giving each student a bomb to defuse. Your mission, which you have no choice but to accept, is to defuse your bomb before the due date. Good luck, and welcome to your bomb squad. Get your bomb. You can obtain your bomb by pointing your web server at... I don't want to do that. This display a binary bomb request from form to fill out. Yeah, okay, this is all just like bullshit. The server build a bomb and return it to your browser tar file called so and so. Blah blah. Save bomb tar file to protect the directory where you can plan to do your work. Then give the command so and so. This will create a directory called bomb K with the following files: readme, bomb C, write up, PDF, PS, log write up. If for some reason you request multiple bombs, this is not a problem. Choose one bomb to work on and delete the rest. Defuse your bomb. Your job for this lab is to defuse your bomb. You must do the assignment on one of the class machines. In fact, there is rumor that Dr. Evil really is evil, and the bomb will always blow up if ran elsewhere. There are several other tamper-proofing devices built into the bomb as well, or so we hear. You can use many tools to help you defuse your bomb. Please look at the hints section for some tips and ideas. The best way is to use your favorite debugger to step through disassemble binary. Each time your bomb explodes, it notifies the bomb lab server, and you lose half point up to a max of 20 points in the final score of the lab. So there's a consequence to exploding the bomb. You must be careful. The first 4 phases are worth 10 points each. Phase 5 and 6 are a little more difficult, so they are worth 15 points each. So the max score you can get is 70 points. Although phases get progressively harder to defuse, expertise you gain as you move from phase to phase should offset the difficulty. However, the last phase will challenge even the best students, so please don't wait until last minute to start. Bomb ignores blank input lines. If you run your bomb with a command line argument, for example, bomb so and so, then it will read the input lines from that text file until it reaches EOF, and then switch over to standard in. In a moments of weakness, Dr. Evil added this feature so that you don't have to keep retyping your solutions to phases you have already diffused. To avoid accidentally detonating the bomb, you'll need to learn how to single step through the assembly code and how to set breakpoints. You'll also need to learn how to inspect both the registers and memory states. One of the nice side effects of doing the lab is that you'll get very good at using the debugger. This is a crucial skill that pay big dividends the rest of your career. Logistics. This is an individual project. All hand-ins are electronic. Clarifications, corrections will be posted on the course message board. Hand-in. There's no explicit hand-in. The bomb will notify your instructor automatically about your progress as you work on it. You keep track of how you're doing by looking at your class scoreboard at so-and-so. The web page is updated continuously to show the progress for each bomb. Hint. Please read this. There are many ways of diffusing your bomb. You can examine it in great detail without ever running the program and figure out exactly what it does. This is a useful technique, but it's not always easy to do. You can also run it under a debugger, watch what it does step by step, and use this information to defuse it. This is probably the fastest way of defusing it. We do make one request. Please do not use brute force. You could write a program that will try every possible key to find the right one, but it's no good for several reasons. You lose half point up to max 20 points every time you guess incorrectly and the bomb explodes. Every time you guess wrong, a message is sent to the bomb lab server. You could very quickly saturate the network with these messages and cause the system administrator to revoke your computer access. We haven't told you how long the strings are, nor have we told you what characters are in them. Even if you make the incorrect assumption that they all are less than 80 characters long, you only contain letters, then you will have 26 to the power of 80 guesses for each phrase. It's take a very long time to run and will not get the answer before the assignment is due. There are many tools which are designed to help you figure out how programs work and what is wrong when they don't work. Here's a list of some of the tools you maybe find useful in analyzing your BOM and hints on how to use them. The GNU debugger. This is a command line debugger, a tool available in virtually every platform. You can trace through a program line by line, examine memory registers, look at both the source code and assembly code. We're not giving you the source code for most of your BOM. Set breakpoints, set memory watch points, and write scripts. The CS APP website, so-and-so is handy, single page GDB summary that you can print out and use as a reference. Here are some of the tips using GDB. Let's go ahead and pull that up. Boom. GDB, I think this is the, yeah. GDB tutorial. And this thing here. Okay. This is probably all I need. Is this the... Okay, maybe I'll read through this as well. Alright. It's good to know those are available. Let's go back here. To keep the BOM from blowing up every time you type in a wrong input, you'll want to learn how to set breakpoints. For online documentation, type help at the GDB command prompt, or type man GDB or info GDB on a Unix prompt. Some people also like to run GDB under GDB mode in Emacs. Okay. Object T, this will outprint the BOM symbol table. The symbol table includes names of all functions and global variables in the BOM, names of all the functions the BOM calls and their addresses. You may learn something by looking at the function names. Object D, use this to disassemble all the code in the BOM. You can also just look at individual functions. Reading the assembly code can't tell you how the BOM works. Although Object D gives you a lot of information, it doesn't tell you the whole story. Call to system level functions are displayed in cryptic form. For example, a call to scanf might appear as this: call some random address. To determine that the call was a scanf, you would need to disassemble with GDB. Okay, strings. This utility will display the printable strings in your BOM. Looking for a particular tool, how about documentation? Don't forget commands, apropos, man, and info are your friend. Particularly man ASCII might come in useful. Info gas will give you more information, more than you ever wanted to know about the GNU assembler. Also, the web may also be a treasure trove of information. If you get stumped, feel free to ask your instructor for help. Boom, boom, boom. Okay. Cool. Let's just throw this over here for now. And full screen this. And I need to take a quick bio break. I'll be right back. Okay, some things to do. We can read the BOM C to get a general gist for like how the program executes from the main. We can run strings on bomb. And I heard that that's not secure actually. So I'm gonna run it in here, strings, bomb. Gives us a bunch of stuff here. We can sort, unique it, and put it into a pager, less. Alright, what we got going on here? We're gonna say, let's run like a new debugger again, and we're gonna run disassemble. How do I disassemble the whole thing? Can I say obj dump, disassemble all, D? Or maybe D like this? Pass that into the pager. There's the connect, sleep, socket. How many lines of assembly is this? Kind of curious. If I do a word count -L, so that's 1,741. So it wouldn't be really optimal for me to understand every function in this binary. It's quite a lot of like manual disassembly where I have to like go through and comment things. So that's not going to be an effective strategy. I say we just run it. I have the networking disabled, so it's not going to do anything. And besides, it's like, welcome my fiendish little bomb. You have 6 phases of which to blow yourself up. Have a nice day. And I'll just do that. Okay, so we do GDB bomb. And B main. Continue. Sorry, R. So we're at main here. So vim up bomb.c. Alright, main here. So anything, there's some comments in here. Note to self, remember to erase this file so my victims will have no idea what's going on. Instead, they will all blow up in spectacular fashion. Doctor, okay, haha. So we have this end file. That's being used up here. Note to self, remember to port this bomb to Windows and put a fantastic GUI. No, I'm not going to do that. When run with no arguments, the bomb reads its input lines from standard inputs. Makes sense. When run with argument file, bomb reads from file until EOF, and then switches standard input. Thus, as you diffuse each phase, you can add its diffusing string to file and avoid having to retype it. Okay. So open up that and put it into infile. Error out if it's not, else. Print out the usage. Okay, then we initialize bomb. So I'm gonna put a breakpoint on initialize bomb. And if I just like disassemble from here, help disassemble. Disassemble breakpoint number 1. Arguments are breakpoint numbers with spaces in between. To disassemble all breakpoints, give no arguments. A disassembled breakpoint is not forgotten, but has no effect until re-enabled. B for breakpoints. No breakpoint when it's disabled also set. Oh, it's disabled, not disassemble. So EN1 B. Okay. Can I do LS? Let's look at cheat sheet. So I'm not terribly familiar with everything. So quit, run, kill, breakpoints, execution. Disass. I have to say disass instead of just this. This is disabled. Bunch of printing. Source. How do I print source? Oh, let's say disass main. Okay. So this is all the moving to in file, testing, call queue, printf, exit, printf, exit, initialize bomb. So we are calling initialize bomb. So I can just say, okay, breakpoint initialize bomb, which is at 401382. Continue. Okay. Disass. How do I find out where I'm at? Where? Okay. So I'm in initialize bomb. Disass. Initialize bomb. Well, if I just say disass, yeah, it does the same thing. Okay. So this thing subtracts 8 from RSP, so allocates 8 bytes, moves this constant into ESI. I need to open the book up to my registers table here. So I'm just going into this because this is the first. Do all sorts of secret stuff. Makes the bomb harder to defuse. So I don't want to do any of that. This is in. So it's setting ESI and EDI. ESI is second argument. EDI is first. So 2 is the first argument. Calls it the signal PLT. And then ESI is probably a handler. So can I say disass 0x4012A0? Yeah, this is a function called signal handler. Okay, so we're going through here. It sets, calls signal with 2. If I go over here and say, I'm just gonna Control Z this, man to signal, and we look for, so it's a signum and a handler. So where are the signals, man? Oh, come on, get out of here. Man signals, signal. What man page are these signal numbers documented on Linux? Signal 7. Okay, that was a problem. Man 7 signal. Okay. What is 2? I need the numbers, please. Here we go, sigint. So that'd be Control C. So that's basically sending Control C to this handler and then resetting that. Okay, so it's basically just setting a signal handler. And then the signal handler does things like putting some string to the screen, sleeping, and printing some other shit, flushing out, sleeping, putting, exiting. Well, let's read through the whole thing here. So the first thing is it expands the stack. It puts this thing into EDI. If you look at EDI, EDI is the first argument. And then it calls puts. So there's going to be a string here. So if I say dis as of 0x 4024 C0. So I want to print out that memory. So let's go over here. It's going to be like a print command of some sort. Where do we do string? String. Print char star. Okay. Let's try that. P char star of 0x4024 C0. So you think you can stop the bomb with Control C, do you? And then it puts a new thing in EDI, it puts 3, and then it's going to sleep for 3. And that puts this new thing into ESI, 1 into EDI, and a 0 into EAX. Interesting. Wonder why it does that. Well, ESI, if we look at dis as, we'll do under print f chk at plt. Oops. I'll just say that then. Not sure what that is. Okay, so looking back at the code here, so it's going to be a 1 and a pointer somewhere. So oh, you can just disable functions? That's nice. I thought disas, if I do help on dis, oh, it's disassemble. Alright. Okay, breakpoints, delete, disable, enable, delete all breakpoints, clear some, execution step I or SI, process through function calls without stopping, step, execute one C statement. Continue, resume execution until next breakpoint, until 3, continue execution until the program hits breakpoint 3, finish, resume execution until function returns. So that'd be like a step out. And then call sum 1, 2, print the values. Oh, you can call functions. Wow. Is there like a symbol? Symbol? No. So I want to know what is that byte here. Where is it here? So I'm gonna do disass and then say 0x4024C0. Print. Can I do like that? 0x4024C0. We'll say char star. So that's still the same thing. Oh, that was the original one. Sorry, my bad. I wanted to see what is going into here. Okay, signal handler did that stupid print. Sleep. It's 402582. 402582. Okay. 2582. Well, so that's what it's moving in to 1, which would be standard out probably. So it's saying print, but it's a printf check PLT. I don't know what this check thing is. 40C. Let's print that thing out. So disassemble. What is it called? Interrupt handler? Sig handler. Sig handler. And then we're gonna disassemble 0x400C00. So this is a jump to this location, and then a push quad word 12 onto the stack, and then a jump to that location. I'm not familiar with that, but it looks like it's taking the instruction pointer, adding this offset, and then dereferencing that. And we're in a very low address range here, along with the sig handler. Sig handler is very low as well. This is like very high in their address range, which is why I was like wondering if this is even the thing that we're calling. Because so far, like main started at 400 DA0, and we've just been in that range. But then when I assumed this was the name, oh, I had 3 underscores. Oh, no, I had 2 underscores in my command, but it assumed 3 underscores. So definitely not the right thing. Anyways, so it's calling this thing through the PLT. So this might just be code for how the PLT works. And this is jumping to printf at got.plt. So we need to go there. So if I so it would be the addition of this with this value. Wouldn't that be known at compile time? Yeah, well, I guess the disassembler is telling you exactly where it is here. I guess because the instruction pointer, because the code can be relocated, the instruction pointer isn't constant. It's determined by the address space layout randomization. So that's why this is computed. But I guess the binary, I guess this instance of the binary, it was mapped to this address. Okay. So let's go ahead and disassemble that, which is 0x603090. So now we got, this is the got. It has a bad instruction. Thanks GDB for that. And then it's saying OR 40 with AL, and then add AL to RAX, add AL with RAX, add DL with RSI. That seems wrong. let's go ahead and dump the symbols again for, oops. Can I just like grab this and move it? Yeah, interesting. Obj dump. I just want the symbol table of bomb. And we're gonna grep for printf chk. Okay, that's a glibc thing, so I don't have to worry about that. So that's like an implementation of printf. So I'm in the weeds on that. Okay, so I don't need to worry about that. Let's go back to doing the signal handler. We can ask AI here, what is fortify source security feature? It performs additional runtime checks to detect unsafe usage, like certain buffer issues. What PLT needs procedural link table. It's used for lazy dynamic linking. When the program calls a dynamically linked function like printf, the compiler automatically calls the PLT stub. The PLT stub on first call jumps to the dynamic linker. Linker resolves a real address in libc. Updates the global offset table. Feature calls to jump directly to the resolve function. Okay, so I'm not going to be able to follow it through there. Anyways, okay, so that's just saying, hey, write the standard out. ESI. What the hell is? That was the well. So I imagine this is like just writing the standard out well. And then this is what is that here? Standard out. So that's the file for standard out. So it's flushing standard out after it wrote well. Since we're using the libc IO stuff. And then we write 1 into EDI. Again, EDI is our first argument. We call sleep again. And then we write this big number, which is another string. So I'm about to say print a char star at that address. Okay. And then it exits with 10. So if I want to patch a function in GDB, how would I go about that? And then over here, what I'm going to do is I'm just going to continue, and then I'm going to try hitting Control C and see what happens. So delete all breakpoints. Yes. And then continue. Then I hit Control C, and it's saying program receive interrupt. And then if I hit, we'll just say next or continue. Restart. Yes. Continue. Oh. Okay, I blew it up because I thought it was in GDB. What I want to do is just run the freaking program without GDB, bomb, and hit Control C. This is all the sleeping stuff. Well, okay, and exit it. So I want to patch that out with GDB. So how would I do this? Just continue, sorry, restart, and then Control C, and then continue. So how do I send a signal? That's the next question I have, because it's clearly not sending it. So signal. Okay, it's not in the cheat sheet. Maybe over here, signal. Signal. Doesn't say anything about actually sending signals. Overwrite instructions at the function entry. If you want to change the behavior of a function, for example, make it return immediately, you can overwrite its first instructions. Example, force a function to just return. Suppose it starts with push RBP on the stack, move RSP into RBP. You can just say set unsigned char, which is 0xC3, which is return. Now whenever my function is called, it immediately returns. Write multiple bytes, patch whole instruction sequence. Example, replace first 5 bytes, return 0. Redirect the function, jump somewhere else. So you can just set it to 0xC3 and it'll return it. That's nice to know. Change return value without patching code. If you only want to override the result, this was function to return 0. So that's a set char my function 90. Whereas this is set unsigned char my function. I like this thing. Set right on. C3 90 XOR EAX ret, which is 31C0 C3. When I hit CTRL plus C in GDB, it intercepts it. How do I ensure the signal SIGINT goes to the traced process? Important caveat. Oh, you can just send it explicitly signal SIGINT. Okay. So let's go here. Okay, there we go. So you can restart. I'm just hitting Control C to get the prompt back, and I'm going to do this thing, and this is going to be sig handler. And then we say signal sigint. So now when I send it, it's like not hitting that signal handler. That's interesting. I'm just playing around with stuff now because like just want to get kind of used to doing some things in GDB. Okay, so we have a way of easily say here. Okay, just put that in there. All right. Disassemble sig. I feel like we understand the sig handler now. It set a breakpoint at main. Restart. Yes. And then next, 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 next. We'll do a dis ass main, and then initialize bomb. Let's put breakpoint on initialize bomb. Restart. Yes. Continue. Dis ass. Okay. Step out. How do I do the step out again? Because if I do SI here, that just goes to A6, SIAB, SIB0, SI B. Oh fuck. Because that was a call. It went to the signal PLT. Okay. Where is the... There it is. What was I looking to do here? Oh, the step out. Continue until finish. Resume execute. Okay, so that'd be finish. Finish. Run until exit of initialize bomb. Disassemble. So we are here, which is right after initialize bomb. So that means that initialize bomb does the puts. Disas initialize bomb. No. Who did that print there? So I go up here, it says, oh, this just tell me like what instruction I'm on. Okay. So disas. So that's putting the string. Another string. So I just put these strings out. If I do print char star, oops, char star there. I don't need the dollar. And this is the other one was 378. Okay. Those are the puts there. It does a read line and then passes into phase 1. So let's set a breakpoint to phase 1. Sorry. Breakpoint to phase _1, my bad. And then we're just going to continue. And then we'll put in ASDF here. And now we're in phase 1. And if we look here, this S, so it's saying allocate 8 bytes on the stack, move this thing into ESI. ESI is, of course, the second argument. The first argument would have been whatever EDI was here. Here it is. So read line returned RAX, it put it into RDI. Okay, so basically the string is what it's comparing it to. So if I print out the char star here of that value, border relations to candidate, and I saw that in the strings output. So what we can do is just save that off here. Say answers.txt. Put that in there. And then what I'll do is, since I have control of this, I'll do step instruction, this S. So now we're in here. And I'll put this into EDI as well, because EDI is the first argument, which will make sure that that returns correctly. So can I do that? Yeah, I can do that, right? How do I set registers? So you can print registers. How do I set register? Set breakpoint. Okay, register. I don't want info register. Sorry, register. Okay. Set REX to dead beef. This would be under okay. Okay. Let's go back over to here. So I'm going to say set EDI, right? EDI is the first argument, yep. And this is going to be a $EDI. Set EDI equal to info registers. Can I do it like this? Info registers, and then we say set EDI. Because EDI is going to be the other string. Where's EDI? RDI. What the hell? Maybe my set went through. Well, disass, and then we say step instruction, disass. I want to do a next to go over this call queue. God damn it. How did I get to there? I want to go next to go over call queue, but not jump into all this shit here. I should have set a breakpoint. We'll do that here. Breakpoint here. Sorry. Breakpoint there. I can't set a breakpoint on an instruction. Breakpoints, maybe it's a 0x thing. Break. Well, let's see if it's in their little help thing here. Breakpoint, you have to say a star. Okay. Star 0x. This thing here. Restart. Continue. Continue. And we're going to say disass. Print out ESI. And print out EDI. Do the same. Step instruction, disass. Now we're going to say print $ESI, print $EDI. Okay, now they're not. So we're going to say set EDI, which is the first argument, right? EDI, yep. $EDI to, can't say $ESI. And then print both of them. There we go, they're the same now. I'm going to say continue. Disass. So I have my breakpoint there. And then print EAX. sorry, print $ex. So that's 0. So they're equal. Step instruction. And then we say dis s step instruction. So now we're going to jump if equal, they were equal, to phase 1 plus 23, which will be the add, I guess. Yep, we're now at the add, and we can continue. Okay. So now we're going to hit Control C, do a dis s. We're in the syscall somewhere. If we do stack backtrace, we figure out where we're at in the stack here. So we're in the main read line. So if we dis as main here, we can see where we're at, I think, right? No, it doesn't give us where we're at inside there. Okay, well, we know we're at the read line at 401 4AC. So 401 4AC, wait a minute. That's not where we're at. 400, no, these are just the functions. 400E53. E53. So we were here, we went. That's where we're returning to. I guess this is the return. So we're saying when we're done with read line here, we're returning to 400E53. Which will take us here into phase 2. So I'm going to just say breakpoint on phase 2. And we continue. And hit Control C here. We'll do a dis as. Oh no, we have to see here. I'll just do ASDF. Now I'll do a dis as. And dump out the assembler code for phase 2. Gets a little more difficult. How does it report? So we avoided the explode bomb. What we can do here is say, hey, dis as explode bomb. And see what it does. So it just does 2 puts and an exit. Probably because they don't want to like deal with like self-study people sending shit to the network. So they just compiled that out. But we can patch this. And now we'll never explode. We'll just return. My function will be explode bomb. Now if we disassemble it, it just immediately return. Alright, so we have one of the solutions. Let's look at phase 2. Please go away. Alright. Dis as, where are we at here? We are in phase 2 at the top. Okay, so it's pushing RBX and RBP onto the stack so that I can use those as a call E saved registers. I should write these down because they're not in the book table that I have. On AMD 64, what registers are call E versus call or saved? And grab my pen here. So RBX jump. Okay. These are all callee saved. Our BX, oh, it says right here, callee saved. And then our CX, our DX, our BP, callee saved. Alright, our 12. Okay, it says it here. The ones that are callee saved. 12, 13, 14, 15. Then RSP is obviously stack pointer, so that's callee saved. So callee saved, our BX, RBP, callee saved, stack pointers obviously callee saved, and then 12, 13, 14, 15. Those are all the callee saved ones, and then caller saved registers are everything else, which is RAX, obviously because that's the return, RCX, RDX, RSI, RDI, R8, 9, 10, and 11. Basically all the arguments and return. But 10, 11 are just temporary scratch that are caller saved. Okay. Alright. I'm going to take a quick bio break here and I'll be right back. I'm gonna be munching on some stuff here, so I'm just gonna mute. Not familiar with this. In the FS segment, offset 28 from the base of FS. The destination register. Thread local storage. Thread control block. Okay. Thread ID. Okay. So we take the, what does FS stand for again? Code segment, data segment, stack segment, extra segment. FG is just everything after E. Okay. Just taking a thread ID basically and storing it in RAX, which is the return, and then moving that into RSP, setting EAX to 0. So I don't know why it does that. Maybe it can't go directly from here. Oh, because this is a memory access here. So we're saying add 78, or subtract 78 from RSP, and then add 68 back to RSP, which gives like a 10 byte value. Oh no, because it's yeah, gives you 16 bytes. Yeah, 16 bytes. Then it XORs EX to reset it, and then it does a comparison long with num input strings. What is num input strings? Oh, it's a bit of memory that got written to, probably. Print out 13. And that's 6. Okay, so we're reviewing the diffusing logic. So I need to reset my mindset because I thought I was in phase 2 there for a second. This is the diffusing logic. The first thing it does is it stores the thread ID in RAX and then stores that into the stack somewhere. And then it takes this thing in memory, this place in memory called num input strings, and compares that with 6. It says, hey, if you're not equal, then we jump to phase diffused plus 123, which would be 40, 16, 3F, which will be down here. Which will then take the 68 value, which was the thread ID, move it into the return, XORs out the RAX. That'll put it back to 0 if the thread IDs were the same, the one on the stack and the current thread ID. If they're the same, then we jump to phase diffuse. Otherwise, we call stack check failed. So that's to make sure that we're on the same thread as when we started. Looks like that's what that's doing. Oops. Yeah. Okay, so that's just stack smash stuff that we don't have to worry about. So basically, if the num input strings is not equal to 6, we just go down to phase diffused, assuming our stack wasn't smashed. So this will go to 654, which will then add back to stacking. Okay. I'm curious where this num input strings is. Because right now it's 13. Let's set a breakpoint at phase 1 and restart. Yes. Continue. If we print out disass explode bomb. So we need to reestablish that. Let's do a normal split. Edit our answers? No. Notes. Edit notes.md, please. Thank you. So we need to redo this on explode bomb here. Oops. The hell? Okay. Okay, that prevents us from exploding the bomb. If we do breakpoints here, disass 0x4013A2. That's initialized bomb, so we can say delete 7, B, delete 8, B, nine. Why does it keep on putting that back there? Delete all. Okay, so this is just here because it's, yeah. Phase 2, phase 1. Continue. And I'll just pull this thing in here. Continue. Okay, I'll kill now. And quit. Yes. How do I do this? Do I do like boom boom? And then answers. Continue. Restart. Continue. Damn it. Restart. I always have to do this here. Fuck. There we go. Alright, restart. Control C, quit. No. Quit, yes, quit. Okay. I'm not doing too well on this. Because I always assume that I'm in the GDB prompt, which I'm not. Okay, so what do I want to do here? I want to specify args to GDB. Okay, well, we'll just do that over here. Args. So you do dash dash args. And you give it the full program, args, program arg list, okay. So this is gonna be like this, args, like that. And then if I do man GDB, what else? Command. Command file. Eval command. Execute given GDB command. Init eval command. There we go. Or maybe just eval command. Let's say Q here. Eval command. Fuck off. Eval command is equal to this thing here, or not that one, this one. 110. Quit. We'll say b main r and then that. How to give GDB commands list. When you start GDB, give commands to run and then continue debugging. I want them to be args to GDB so I don't have to retype them. Okay, so you can do EX multiple times. Okay. Quit. So this is going to be EX here. EX. Breakpoint on main dash EX. Restart. And then dash. Is it dash EX? What the fuck? Doesn't seem right. Okay. Says EX. So you set a breakpoint main, we restart, and then we I think we need a restart first, right? EX, restart. No. Quit. Yes. EXR. Dis as explode bomb. Yep. Okay, cool. So that'll get everything set up correctly. Okay. Yes. Okay. So this is when we have to breakpoint phase 2. Oops. Phase 2. Continue. Dis as. Alright. So this is a function for phase 2. Saving off RPRDX, putting 28 on the stack. RSI, which is the first argument, will be our stack pointer. Actually, then we call read 6 numbers. It's going to read 6 numbers. Let's put a breakpoint on read 6 numbers. Continue. Dis as. So this thing will explode the bomb itself. So it's getting handed the stack pointer, which has 28 it's calling scanf and then going to 99 or exploding the bomb. So there's 5 with EAX. So something about scanf not returning, it explodes bomb. It's basically if it errors out. So what do we do here? We subtract 18 off the stack pointer. We move RSI into RDX. RDX is third argument. So we move the second argument. Wait a minute. RSI to RDX. What the fuck's going on there? RSI was here. Read 6 numbers. RSI is the second argument. DI is the first argument. And if we print out RDI here, that's just some big number there. If we go back to main, if we do a backtrace and we go to dis as main. So before we went into phase 2, the return of read line went into RDI. So RDI is the return of read line. And that's the first argument to phase 2. So then if we print out, or sorry, dis as phase 2, it keeps RDI. It's the output of read line. And this read line, oh, this read line is like I need to disass that. Sorry, read line. Because this is like not your standard read line. Yeah, let's go ahead and disass main. Come on, let me have my computer back, please. Alright. So when we go into reline, we do our puts up here. EDI is the first, yeah. So readline just gets the same string as was sent to puts, but it probably ignores it. Okay, so let's go back and readline. So it puts 8 on the stack, 8 bytes on the stack, puts 0 into the return, and then it calls skip. Disass skip. What the hell? Return from more quit to quit, C to continue without paging. This is a big ass function. What does this thing do? Skip. Well, it doesn't explode. It does a zap char. The fuck is zap char? Well, let's just step through it. So I'm in read 6 numbers. I'm gonna restart. Breakpoint on, let's see where all our breakpoints are at. B, so delete. Yes, B phase 2. Continue. Phase 2. And we'll just do like, hey, disass where we're at. So a step instruction. Is there a easy way to run step instruction and disass in GDB quickly? Oh, TUI. There we go. So that would have blown up. Oh, that's interesting that when I restart, it blows away my stuff. Um, I'm gonna put a breakpoint on explode bomb as well. Oh, you have to. Oh well. Yeah, I just I'll disable this checkpoint thing here. It's not needed. Okay, so run it. So to get the breakpoints in, I need to do it that way. Okay. No? Why did this start to fail? I thought we had that one solved already. This TUI is getting to be kind of annoying. Huh. Explode bomb changed. Phase 2. Thought I had this one solved already. Well, what we can do here is say yes. Just delete off the answers. Continue. One, 2, 3, 4, 5, 6. That's gonna explode it. Okay. Set a breakpoint on phase 2. I thought I had this thing done. Restart. Yes. Continue. Do this guy here. Oops. Sorry. Disassemble. Actually, what I'll do is I'll delete this, save that file, quit this, yes, rerun this. Okay. Step instruction. We're in main. We're going to continue. We're going to restart. Breakpoint on phase 2. Continue. Sorry, yes. Breakpoint on phase 2. Continue. 1, 2, 3, 4, 5, 6. Restart. Continue. Let's try Clang. Clang, LLDB. Apt get update. Sudo apt get update. Is this that old? Okay. Okay, I guess we're stuck with GDB. Just this TUI thing sucks, man. It really sucks. Alright, disass. I'd rather just disassemble everything. Continue. 1, 2, 3, 4, 5, 6. Nope. Breakpoint on phase 2. Restart. Yes. Continue. Continue. Phase 2. Disass. So RSI is second argument to read 6 numbers. 1, 2, 3, 4, 5, 6. Four, 1, 4, 9. Why would you get 5 out of scanf? Maybe it's 5 numbers? Jump greater than, read 6 numbers. If we print out EX, okay. Restart, yes. Continue. 1, 2, 3, 4, 5, 6. I'll put a breakpoint on star 0x 40148F. Continue. Dis print out dollar $EX 6. Continue. Well, we're not going to continue. We're at step. So you got past that one. So this was right as far as there being 6 numbers, but it's probably just some math on the numbers. So we'll do, how do I bounce out? Finish? This S. 1 with RSP. If you print out RSP here, and if you print out the dereference of RSP as a char star, or we can just print it out like that, right? Did I do a star here? Maybe? Yeah, I want to dereference a generic pointer. Okay. Oops. Oh, you have to give it the type. Examine the such X thing. X word RSP. So can I do X B RSP here? Long word double quad. So you got word, which is 4 bytes. 8 bytes is a G. Why is it a G? A gigaword. We'll do G. B seemed to work. G. 2 words. We'll do 6 words here. Yeah, 1, 2, 3, 4, 5, 6. So because it's doing RSP, comparing 1 to RSP, and it's a long, and a long in this context is bigger than a word, so it'd be 32, I believe, because a quad word is 64. So long would be 32, which would be 4 bytes, which would be a word in this. So it's saying 1. Compare 1 to that, yeah. And then, so if I SI here, dis S, so the comparison SI, it's going to jump, dis S. So you came all the way down here, and then we say, hey, look at 4 RSP. So that was at RSP. Look at 4 RSP, RBX, and 18 RSP, RBP. So we're loading some addresses into these registers. And then we do a blind jump to 27, which is F17. So we go back up to here. So we'll say SI, 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 dis S. So now we're up here. We put RBX minus 4 into EAX. We add itself with itself. And we compare it to RBX. Jesus Christ. Okay. So RBX was this guy here, which was, well, we can just do the comparison here. What is this RBX? Print out the $EAX. So that's 1. And now it should be 2. What is this? Dis S. So you compare 2 to RBX. If we print out RBX, and if we examine the word at RBX, it's 2. So that's going to jump us to 41, which is 25. So we're not going to explode there. So 1, 2 is so far correct. Is this a Fibonacci sequence? Dis S, where are we at here? So we're going to add 4 to RBX. So print $RBX. So RBX, wait a minute, what? Add 4 to RBX? Oh, that's the memory address, RBX. So if we examine word $RBX, and if we say 4, I can say 4. Can I say plus 4? Like this? 3. So we're going to add 4 to 3, and then we're going to compare RBX to RBP. Sorry, print RBP. RBP. Wait a minute, what? We add 4 to RBX, and it should point to the same places. RBP. Fuck, man, this shit's hard to understand here. So if we print out RBP and print out RBX, they're different. jump to 64, jump FC3. That's our exit case there. So we got to reverse what happened here. So we went through these instructions here where we're like, okay, RBX is going to be the stack pointer plus 4. RSP is going to stack pointer plus 18, RBP. And then we go up to 17 here. We then do this thing, which we pass. And then we jump down to here, 25, where we take 4 and RBX is here. So we say add 4 to RBX, which is RSP plus 8 now. And we compare RBP to RBX. How could that ever be 8? Wait a minute. 8 plus 4, 8, 9, 10, 9A, B, C. Yeah, before. This one's tricky. So we read 6 numbers. Clearly, first 3 were important, but I think we need more storage on the stack, maybe, because it's doing all this stuff with the stack here, the stack pointer here. It moves offsets of the stack pointer into here, jumps into 17. This is just some math with EAX, which is irrelevant. Oh, but then it does a comparison with E, which is irrelevant. Doesn't do any mutation. So this is just mutating EAX, which is fine. And then we jump down to 25 here to explode get over the explode bomb. We add 4 to the RBX, so that's RSP plus 8. And we compare that with RBP, which is RSP plus 18, which will never be the same. And then we jump to 27, which is 17. We jump back to 17. Okay. So we're not dead yet. So we go back to 17. We do some math. I don't see how we escape this though. So if we disassemble, disas, so they're not equal. So we're going to jump to 17 again. Okay. We then, okay, so RBX is now, all right, we're subtracting 4 here into EAX. So this is, it's not mutating RBX though. If we print out $RBX, it's still 7,000. It's been 7,000. If we print out RSP plus 4, so RBX is a 7,000 here. I think I printed it out up here too. 7,000. If you subtract 4 from that, it would be 6,000. The 0 would become a, wait a minute, let me just pop open pop up in Python here. 0x7000 minus 4, 0x4, and then view that in hex. 6 FFC, which is not the stack pointer. Is the stack pointer changing anywhere here? RBX does change here where we add 4. I forgot about that. So we jump down to 25, we add 4 to RBX, do the comparison. Okay. So SI here, and we'll see what EAX is now. To print out EAX, this is 2, print out RBX minus 4, print out or examine word RBX 3. So I think this needs to be a 2. Okay, I think 122 is the right thing so far. And then I'll put 9s for these because we don't know them yet. 9, 9, 9. Oops. Okay, and we're going to restart. Yes. Continue. Phase 2. Disassemble. We're going to get past the read 6 numbers. So next we'll go to dis s RBX. Okay, that next went all the way past, if we BT here, we're in read 6 numbers now. Wow, that was quite the jump. And that's only because there's a breakpoint there. Okay, so we have this, Jesus Christ, scanf. If we SI here, this S, SI, this S. Okay, so we're gonna finish this S. Okay, I think I had a breakpoint there, which is why this 48F1. Okay. How to list all breakpoints in GDB. Info B. That's what I've been doing wrong. I've been using B instead of info B. Kill these. Info B. So the read 6 numbers, so delete 4, delete 5, info B, phase 2 plus 14. Okay, delete 6, info B. So we have our main, our explode bomb, and our phase 2. So now I can restart, yes. Continue to phase 2. Next. So if I dis as here and I say next, I should go to line F0A. No, I went to explode bomb. I wonder how that happened. What does next do in GDB? What if you call next when you are on an instruction that is not a call instruction? That's not what happens. I called next and it went way the fuck over. Alright, restart, yes, continue, disass, SI, disass. This should be next, F0A, nope. Oh, because read 6 numbers blew up? Disass. Am I inside BT? No, I'm inside phase 2. I'm on 14.3a. Inside phase 2 is F25. So this is the explode bomb here. Okay, I want a breakpoint here. And I have to do a thing like this, right? A star. Restart. Yes. Continue. Continue. A B or disass. Print out, say like REX. Sorry, print out $REX. So you are 6. Compare 1 to RSP. Okay, so we're in the heart of phase 2. Okay. So the first thing is say, hey, is 1 in RSP? And indeed it is. And then we jump if that's equal down to our little thing down here where we set up, so I'm just going to print out RSP, print out RBX. Actually, let's do, yeah, print out $RBX and print out $RBP. These are mostly junk right now. But if we SI, or disass, so now we're going to have, if we print those things out again, stack pointer, fuck is this thing? Examine 2-word hex, 2W or GX maybe? GX. Okay. But why can't it give me back the memory address? RBX. So inconsistent. How do I print out the contents of a register in GDB as a hex if it is a pointer? Print X, PX, not examine, but P. Okay. PX RSP, PX RBX, PX RBP. So the stack pointer is at 30, 34, and 48. And then if we examine word 6, is it word? Yeah, word 6 from, we'll just do a stack pointer. Yeah. Maybe do 6 words. Okay, so our stuff is on the stack as we expected. 0. I did 1 to 2 there. Okay. And BX is at 4, which is this one here. And BP is at 8, which is this one here. Okay. So this S, we're now going to step here, this, which I know it's going to send us up to 17, which is here. So we're going to subtract off from RBX. So RBX would now point to the 0th element. And we're going to say store that in EAX. Right? RBX is essentially pointing at the stack now. This as SI. So this should be 1, right? Print out $EAX. That'd be 1. And examine the word at RBX. That's 2. So that's going to fail. Oh, but it adds it to itself. So we went back, we say, hey, add it to yourself, and then go to the next one. So that's going to pass. So we go down here, we add 4 to RBX. So before RBX was at 4, so now it's going to be at 8. So let's print out all that stuff. So first we do our thing here, okay. BP, BX, SP. So our SP BX and BP. Okay, we're still like that. So we're going to add 4 to that, which will take us to the BP. And then we're going to compare RBP, and that should be true, right? This ass here. RBP and RBX. If I print them out, 1. Oh no. We're at 48 here. So we went from 34 to 38. So they're not going to be the same. So now we go back here. We do the subtraction. So this as, we're going to say, hey, go back 4, look at 2. So EAX is going to be 2. and then we're going to add it to itself. Okay, so it's going to be doubling it every time. 2, 4, 8, 16, 32. I'm going to restart from here, and I'm just going to continue. Sorry, restart, yes. Continue, continue, continue. Okay, that's it. We'll hit Control C, breakpoint on phase 3. And then we'll just say continue, read a bunch of garbage. We'll do a dis ass on this. So it also does a scanf and has a bunch of checks. So just looking at this thing, it takes the stack pointer, adds 18, and then let's just print out what the printf format string here is. So we say print as if it's a char star. This thing, sorry, doesn't need the dollar. There we go. So it's DD. So say 99, which means we'll have to restart here. I'll go ahead and save this file. Oops. Let's do it like, let's pull this guy down here like that. Okay. Restart. Yes. Info breakpoints. Delete. Let's see. We want 3, 7, and 8. Oh, 3 and 7. Delete 3. Delete 7. Info B. So you have phase 3. Continue. All right. Phase 3 will be disassemble. And we want to get after the call Q here. So if I print out, or if I examine, actually, let's just go to, so these are the memory addresses it's going to be printing it out to, or saving those things to. So let's go to this address here. So we'll just say breakpoint there. Sorry, I have to do a star. And then continue disas. And then if I print out or examine, what is that? RCX? No. I guess that's the same thing as that. Yeah, let's examine RCX. Print out RCX. RCX is the 4th argument, so it might have mutated it. But we have our stack pointer, so we can say examine a word maybe from this location here. I can say that hex plus RSP. RSP plus 0xc. Sorry, plus 0xc would be, well, A would be 10, B would be 11, C would be 12. So maybe I can just do decimal 12. Can I do it like this, maybe? Oh, it's because of that stupid thing. Okay. $. And then I'll probably have to convert it to this. There we go. So 9 is located there, obviously. Oh, I should split these up. So I'll do like 8 and 9. So restart, yes. Info B. Let's go ahead and del 8. Continue. Dis as. And we got our stuff here now. So I can say print or examine word from this. is 9, and then 8. Plus dollar would be 8. So 8 is stored lower on the stack, or higher on the stack depending on your, but lower in the address range, and then 9 is stored above it, and they're both 32-bit. Okay. So then we're gonna say compare 1 to EAX. Just print out EAX here. Should be 2. Interesting. Jump greater. Oh, because it jump greater than. All right. So this ass. So he jumped over the explode bomb. That's good. And then we're gonna compare long word 7 with 8 RSP, and 8 RSP is our first value. If we print that out again, it's gonna be 8. So we want it to be 7. Jump after though, that's fine. We go to phase 3, 106. 106, which is FAD. And it explodes bomb if it's above that. So you want it to be equal, I guess. So this needs to be something like 7. So when we compare those two, it's not after. And then we move that value into EAX, and then we jump into this location, 2470 plus RAX times 8. So we got to figure out 402. What is that here? This ass. Sorry, I need a. Plus RAX times 8. That's probably going to be a jump into like some random garbage memory, if I can even get there. So I'm going to hit restart on this. I'm going to hit my, put a breakpoint at this address. Restart. Yes. Breakpoint at this address now. Info breakpoints, and we want del 9, and we just want to continue to there. This ass now, and if we print out that 8 value again, it should be 7. Shit, it's 8. Did I not write this? Let's write it. Restart. Yes. Continue. This ass. And now our 8 value should be 7. So then if I step over that, step of that, it's now this ass. It jumped. It didn't jump to phase to AD, which is the badness. Instead, it's taking that value, it's putting in EAX, and then it's jumping to that location. This ass. Okay, and it got down to here, which is interesting because if I print out RAX, it's just 7. 7 times 8 is 56. 56 plus, say 56 plus 402, 470. Is 420 is not this address at all. Oh, but it's in hex. That's what I'm missing. Hex, thank you. 402, 488. It's not that at all. So something's wrong with my math here. So RAX, if we go back to that instruction, so it's 402, 470 plus RAX times 8. RAX was 7 times 8. Let's see if AI can tell me. Where is this instruction jumping to? Okay. Indirect jump means it jumps to an address stored in memory rather than a fixed address. Yeah. Addressing mode. Displacement. Base. Index. Scale. So the number address being read is target address. I don't know if you got this right here. 402, 470 plus, yeah. RX is definitely 7, yeah. 402, 488. Oh, that's where the jump table is located at. So that has the addresses. So I need to print out the jump table, the actual table. Okay. So that makes a lot more sense. So can I just do like a print, or sorry, extract, how many words? We'll do like 10 words from this address here. So FA6, and these need to be quad words, which I think were G's. Yeah. So there's 8 of them here, it looks like. If I do -8 here, $16. Oh, it looks like there's 8 of them. And 1, 2, 3, 4, 5, 6, 7, 8 maybe. So we got F7C, F7C, which is this instruction. And then we jump. 83. 8A. What's this FB9? FB9. I'm going to have to copy this thing here from phase 3. And I'm going to have to go over here and I'm just going to edit a file. We'll call it phase 3 dump. Phase 3 dump dot S? No. Yeah, we call it S. So I just want to do this because I want to be able to annotate this thing. So the first thing would be F7C, this thing, and I'll say here 0 jump target. Just fit it in here. There we go. Okay. The next one is FB, because if I do this plus 8, it give me FB9, right? Yeah. Okay. So FB9, FB9 here. Come on. This would be 1 jump target, and then 83 will be over here. That'll be 2 jump target. 8A, 3 jump target. And then 9-1 be this one. 4 jump target. This will be F9-8. 6 jump target. Oops. Sorry, 5th. So yeah. F9F. 6. And then FA6, this one, 7th. So let's look at what it's doing here on these. So it moves some constant into EAX and then does a jump. These all jump to the same location, which is 400 BE and 400 FBE, which is down here. Oops. Okay. They all jump to there, one way or another. This thing will explode the bomb. So that's FAB. FAD. I don't see that anywhere, but it might be a default. Is there an FAD anywhere in this file? Sorry. Yeah, it's up here. Explode bomb. So we got past that, right? If we do our disassemble here, we are in. We move because we had what value? What value did we have in there? 7? Because we had 7 in there, we went a 0. We went down here, I believe, right? FA6, yeah. We put that, and then we jumped to 400 FE, and then, sorry, down here, we jump down here, and then we compare 0 with RSP, sorry, 0 of RSP with EAX. we set EAX and we compare 0 to RSP. So that, what is this thing? This would be extract word from 0xc plus $RSP. So that's our 9. So 7 was used for the jump table, 9 is using for our comparison. And if they're equal, then we jump down to here and we return. Okay, so I could do 7 and then just say here, what is this, 147? And that should get us there. So if I restart, no, info B, del 10, info B, and then continue. Oh, we hit explode bomb. Okay, so let's put our breakpoint back. B star that, restart, continue. Yes. Continue. I'm gonna continue here. Yeah, okay, restart. Did I save this? I wanna make sure this is saved. Because it's 140, oh, it's hex 147. 0x147, which is 327. 327, bam. Okay. No. Info B, del 11. Restart, yes. Continue. There we go. Halfway there. Okay. Then we explode. So breakpoint on phase, what is this, 4? Restart, continue. So yes, continue. There we go. Disassemble. Okay, we're gonna do another scanf. So we get the format string here, just print out whatever's at this address, which you have to say, hey, char star there. So that's another 2 numbers. Just pull this thing down. We'll do 10. I like doing the smaller numbers, so we'll do 8 and 9 again. Okay. So let's go ahead and restart. Yes, continue. This S. And then looks like we give ourselves 3 spaces on the stack for quad words. And then we store in a value there. No, we pull out those values. So that's storing in those values into RCX and RDX. And then we move that, we do our call Q. So these are getting references to that bit of memory and calling printf again. We've seen this before. So I'm going to set a breakpoint at here and continue this s and say, hey, print out EAX. It's 2. This will go to 1035. I might as well just copy this, right? And go over here and say phase 4 dump .s. Paste it in here. We pretty much know what's going on all the way up to here. So this is jumping to this address. So it'd be 1035, which is going to be explode. Explode. And then we do a comparison between the first value was RDX. RDX is, wait a minute, RDX and RCX. RDX is the 3rd, RCX is the 4th. So scanf probably had 2 other arguments already. So the third, our dx would be the first number, which is 8. Okay, so we're looking at that. So that'd be currently the value 8 as well. And then we say jump BE. I'm not familiar with that jump mnemonic, but I do have the tables in here. Jump BE is below or equal. So unsigned below or equal. If it's eight compared with E, so it would be 8 minus E, and that would be below. No, that would be above, right? Because it's unsigned. I think that fails. I think we need to set E here, because it's going to jump us down away from the explode. So let's just go ahead and set it equal to E, which is 14. And that'll get us past that. So let's go ahead and restart. Yes, continue. This ass. So that'll get us past the exploded bomb here. Ideally 3A. 3A will get us down to here. So I'm going to set a breakpoint on star this. Continue. This ass. Sorry. Continue. Okay. So now we're down here. And then we move the E into EDX. And then we say move 0 into ESI. EDX and ESI are the second and third argument again. And then we call Q func4. So we load up three things here. This as func4. Okay. This is no, it's not recursive. So we load up three things here. Let's document this. So this call EDX is going to have, so this is EDX third argument. It's equal to 0xe. ESI, which is second argument, is equal to 0. These things that cannot be changed. And then finally, we're going to say EDI, which is the first argument, is equal to RSP offset by 8. And that's going to be our 14, which is the same thing as 0xe. So if we just continue down to here, just 1048, so breakpoint, continue, this as, and I just want to print out EDX, print out EDI, and print out ESI. So I have all those right. So we're going to step into func4. This asks this guy, and we're going to need to do some analysis on this. So what the fuck is this thing doing? Func4, and this guy is giving us stack space, moving moving EDX, which is going to be 0 is 14 into EAX, subtracting ESI, which is 0, 14 minus 0, and then moving that into ECX. ECX is just a fourth argument. temp is equal to 14. And these things we can't really control because these are just constants. EDX, ESI, they're just constants. So I don't know what they're cooking up here. But then we shift right on ECX by 1F. So 0x1F is 31. Oh, so we drop all the bits except for the sign. Drop all bits on ECX other than sign. I need to add comments here. That's clear. Okay. So it drops all bits except for the sign on ECX. And ECX is temp. And then we add the sign to EAX. So again, this is just like, unless they're jumping back up to here, let's see where all the jumps go. So this is going to FF2. So this is the first jump target. So that's FF2. So we jump to first. We say jump to 1. And then there's another jump here. This is a unconditional jump. Going to 2, jump to 2, which is 1007, which goes down here, and that just like exits. So this is a return jump. Jump to rets. So we actually do want to do that jump. This is another call. It's a recursive call. It is a recursive call. Yeah, I thought it felt recursive. So this is a recursive call. Recurse. And then this one here too. Recurse. Okay, that explains why these things are constants at first. So what did I have control of here? Was the first argument? Yeah. Which is EDI, which isn't even used here. So the second argument and the third argument were constants. My influence doesn't even have any effect until here. So we just add a comment here and saying my first arg here. All right, we're adding ECX with EAX. So that's a sign bit. It's going to be set to 0. EAX. Right, is plus equals 0. Temp, technically. And then shift arithmetic right EAX. which in this case, if you have the value, what value is this? Temp is going to be 14 plus, the temp is shifted off to 0, so it's 14. 14 right shift by 1 is 7. It's divided by 2 effectively. Divide by 2. Oops. And then here, so we load an address up into ECX, which is the fourth argument, which we're not using. Oh shit, man, it's almost 2 o'clock. I should take a lunch break here. This isn't easy. Been working on this for 3 hours. I only have 3 solutions, and they're the easy solutions. So it's going to be a little while longer for me to reverse engineer all this stuff. But it's good practice. Having fun. So yeah, I'm going to take a break here, get some lunch, do my cardio, and get back on. Probably around 3 to resume doing this. Cool. All right, I'll be back later. Bye.